This podcast is brought to you by LMU Munich.
Hello, everybody. So we started to discuss a little bit the content of Lecture 4. You remember the title of Lecture 4 was the black hole as a quantum state. And we just started to discuss a little bit a few ideas. So I wanted to give you an overview of what I would like to present in this lecture. The nature of the lecture will be slightly different than the previous lectures, because in the previous lectures we were very pedagogical and explained all the details. This is about, in part, about more recent results, and so I will be less detailed. I will try to explain the ideas, but for the details I will refer you to the papers. Okay? You're of course welcome to ask questions if you feel that a certain detail is important for your understanding. So the lecture is based on this paper plus many other papers, mainly with Joy Medved, but also with Lasma, Alberta, and Andre, which some of you may know. They were students here and now are postdocs. This is to appear. Okay, so we already saw, and I will just remind you shortly, that approximating a physical black hole, so that's finite mass, by a strictly classical geometry this was, I remind you, this is setting the parameter that I will soon repeat, this, the dimensionless H bar. If we set that to 0, we treat a physical finite mass black hole as a strictly classical geometry, we find problems, and my suggestion is that this approximation, this too crude approximation, is the origin of the information paradox. And I will try to convince you, or to show you why is it that I think that this is the origin of the information paradox. If I get away from that approximation, we find that the emitted radiation is weakly coherent, and I will explain. This is actually a calculation that I will try to reproduce, what this means is that we saw in the Hawking calculation that the density matrix was thermal. There were no correlations between particles that were emitted at different times, and no correlations between particles that are emitted at different frequencies. Okay? And what we will find is that if we move away even a little bit from the approximation that CBH is equal to 0, we will find that the off-diagonal elements in the density matrix are non-vanishing. And so, in this case, we will not be able to conclude that the state is mixed. And we will see that the actual perturbative parameter that is controlling the purity of the emitted radiation is the number of emitted particles times this parameter CBH. And when this parameter becomes order 1, this happens at the page time, and that's where the radiation starts to purify because of this weakly coherent effects. Now, the other point that we have to remember is that when the black hole has a finite mass, if it has infinite mass, and it is emitting particles, its mass remains infinite, right? If I have an object with an infinite mass, and it is emitting particles, its mass nevertheless remains infinite. So I cannot tell any time dependence in this case. So the approximation CBH equal to 0 corresponds by definition to an eternal black hole. I have no scale to measure time with because the mass of the black hole is infinite. Its evaporation time is infinite, the page time is infinite, everything is infinite. I have no scale to determine its time dependence. But if the mass of the black hole is finite, the black hole is time dependent. Because it has a finite mass, it is emitting particles, its mass is decreasing, and I can tell the difference that after a while the black hole has a smaller mass, a smaller Schwarzschild radius than it used to be initially, right? So in that case, I will argue that because the black hole is time dependent, the energy density in the near horizon region is finite and small. And I will explain, I will try to quantify what small is. So I'm arguing that the conclusion that when you try to, let me say this. We saw from the firewall argument that the near horizon region of the produced pairs cannot be a maximally entangled state. It cannot be a thermofield double, right? You remember that? This is what we did in the previous lecture. And this is a true conclusion, because otherwise information cannot come out. But now the energy density of the near horizon region is not 0. But how big is it? For that I need a scale. And if I'm looking at an infinite black hole, I don't have a scale. Everything is infinite. So if I find an infinite energy density, it doesn't mean that when I move away and discuss a physical black hole, that infinity remains infinite. So if I'm able to look at the finite mass black hole, I can calculate the energy density near the horizon, taking into account the fact that it is not a maximally entangled state, and I can convert that into energy scale. And this calculation I will not do, but I will explain what is the conversion factor between the number of disentangled pairs and the energy density near the horizon. Okay? And this we verified, it has to be the case, that the from QFD. And in fact, what we find is that the deviation is proportional to n rad CBH divided by 1 in one way of thinking about it. I'm not explaining, I'm just stating a result here. So initially, the state of the produced pairs is almost maximally entangled, as the page curve is telling us, right? Because I know that when I trace over the ingoing particles, I get something that is almost thermal. And then eventually, after the page time is reached, the radiation has to start to purify. So what we find is that at the page time, the deviation is a half. So instead of maximally entangled, you get to a half maximally entangled, and then the entanglement in the pairs goes to 0. So eventually they are produced in a state that is almost a product state. This is what we find, and this is how things should work. So that part of the firewall argument is we see it concretely, and it is correct. Yeah. This is the S pair. Okay, so initially it's 0, and eventually it's 1 and a half. Okay. The other so we know that in classical geometry, infinite mass black hole, we have a region, a surface with an infinite redshift, right? Now, if you think about it, you will convince yourself immediately without any calculations, but hopefully I can get to doing some calculations that will support that, that if you have a finite mass black hole that fluctuates, the position of the infinite redshift surface will also fluctuate. Now imagine that you have an infinite redshift surface that is not absolutely sharp, but fluctuates. You always have some finite probability. It could be very small, but you always have some finite probability to be on the right side, correct side of this surface, so that the redshift where you are is not infinite, and you can reach infinity in some finite time. Okay? So once you accept the fact that you have a physical, fluctuating, quantum mechanical, fluctuating black hole, you have to accept the fact that you cannot have infinite redshift. You can have large redshifts, but not infinite. It's the same infinity. Well, in this case, the infinite redshift is replaced by 1 over this perturbative parameter, CBH, that measures the quantumness of the black hole. And another consequence of this is that black holes have some here. Again, I'm not sure if I'll be able to finish that, but there is a wonderful calculation showing, proving in a few lines why black holes don't have hair just from solutions of differential equations in the background. And when you accept the fact that the black hole fluctuates, you see that that conclusion cannot hold anymore. And I think some aspects of these properties will also be discussed by Gia Dvali in the last lecture today from a slightly different perspective. Okay, so let me remind you that we defined yesterday a parameter that was essentially where lambda black hole was the quantum number of the black hole, and this parameter turned out to be 1 over the black hole entropy. So from this perspective, the size of the black hole determines how quantum it is, which is very reasonable. The big black holes, those that have large entropy, are very classical. Small black holes are quantum. And you see that this number, CBH, becomes 1 for, in this context, for a Planckian-sized black hole. So this parameter actually fits our understanding of how quantum black holes should be. And it's the standard definition of quantumness for any object. Another thing that we discussed yesterday is that when we are calculating expectation values of operators, we really need to calculate this expectation values, so the expectation values of matter operators in the full wave function of the black hole in matter, and that this is correct. This corrects the quantum field in curved space-time result, which we denoted OMC, which is obtained by setting the geometry, the metric to be some classical metric, and taking the wave function to be a function of that classical metric, which is the calculation that we did when we did the Hawking, when we repeated the Hawking calculations. Our OM was B Dagger B, or powers of polynomials of B Dagger B, and we used the classical Schwarzschild geometry for the definition of the matter wave function. So, for example, we used 0 minus, right? One state was 0 minus. This was a state of matter that was defined on a background of a classical geometry. Okay, so this 0 minus or 0 plus are both examples of a state of matter which is a function of a classical geometry. It doesn't include any quantum corrections coming from the geometry itself. Of course, the quantum fluctuations of matter can induce quantum fluctuations on the background. This is called back reaction. But here, this is the inverse of back reaction. We are looking at quantum fluctuations of the background and their effect on the operators of matter. And what we found was that in case where this OMC is small or is vanishingly small, the quantum corrections from the background become the dominant corrections, right? So we have to include them if we find that the classical values vanish or are much smaller than CBH. We have to include the CBH corrections because otherwise we're making a large error. Okay? And this clear? Questions on this? No. I think it's hard to argue with this type of logic. The only question is how to implement this calculation. Because the tools that you know are not adequate for doing that. We only know how to do quantum fields in curve-size prime. We read Beer and Davis, we read Slava's book, we read all that, and it's telling us how to do this. Not how to do this. So what I would like to do is teach you how to do a calculation like that. But before we start doing this calculation, let's try to try to understand what does it mean to take a semi-classical or quantum geometry, okay? And I asked just before the lecture yesterday ended about what happens to a motion of a test particle in a background of a superposition of masses. And you answered that I should look at superposition of geodesics. But it required some adjustment. Okay, so let's try to be a little bit more concrete about that. And let's try to think about an experiment where I have, let's say, two spherical masses. It's actually possible to do this experiment in the lab, although I don't think it was done. And it's actually quite interesting. So like so. Suppose, so this is my picture of a superposition of two masses. This is one state, so let's call it 1. And this is 2, right? So 1 is when the masses are on the vertical axis, and 2 is when the masses are on the horizontal axis. And I would like now to find the motion of a test particle, it could be a classical test particle, in this background. Okay? Now, first of all, I want to reassure you that this type of superposition can actually be created in the laboratory, right? Anybody has an idea of how to do that? No? Well, but let's think about macroscopic bodies. So we want to set macroscopic masses in a superposition. Well, in fact, we have an experiment, a running experiment that does that. It's called LIGO. So imagine that I have some optical system, laser or something like that, that I set in some quantum state. That you understand that I can do, and I can do it I can take a macroscopic optical setup and put it in a pure quantum state. Right? You agree? If you don't, then you have to relearn quantum mechanics. And that's what LIGO does. LIGO, in fact, is a state of coherent light over distances of 4 kilometers each. And the number of photons that are coherent there is about an Avogadro number. So it's really a macroscopic quantum state. Now, these photons are hitting mirrors, right? And when they're hitting the mirrors, if I actually leave the mirrors alone, if they float around, they would move. So the photons will put the masses that they're interacting with in some quantum state. Okay? And so this way I can actually create that. There are also nicer, very nice ways of doing that with switches. So suppose that you have a big mass and you have a quantum switch, a device that is coherent, is in a pure state, but in a superposition. And depending on the state of that quantum switch, I can direct one mass here and another mass here. So the motion itself can be almost classical, but the state that I'm creating is still a superposition. Right? So this, by the way, if you thought that quantum mechanics applies only to the microscopic world, you have to rethink. Quantum mechanics applies to all bodies in our world. Sometimes they are not in a state that we can detect the coherence very, very well, but quantum mechanics applies to everything. Okay? So this way I can use it. So in this case, I can actually create a superposition like that. And of course, in this case, if I have a test particle that moves in this background, under the influence of the gravity from these little masses, it cannot move on a single geodesic, right? So I have to now think about what does it mean. It's like a Stern-Gerlach experiment, but it's gravitational one, right? So in this case, of course, if I actually want to do the experiment, I have to be able to prepare the state many times and do some statistics with the motion. But it's not that different from doing a Stern-Gerlach experiment. Okay? The reason that I'm trying to induce you to think about that is because the situation with a quantum black hole is even more intricate. But nevertheless, if you accept the fact that you can have a gravitational superposition like so, and the motion of a test particle in this type of superposition cannot be just geodesic motion in one of these configurations, then you have to start to think more deeply about what does it mean to have a quantum black hole. Okay, so let me, and here you see clearly the difference between back reaction and what I call the inverse of back reaction. So back reaction here would be, suppose I put a quantum particle with a wave function. So it will interact with the masses. And if we consider that these masses are classical, nevertheless, the position of this passing particle will fluctuate, and this will induce quantum fluctuation on the masses. If the mass of the particle is much smaller than the mass of these big masses, the effect will be very small. So this is the analog of the effect of quantum fluctuations of the emitted radiation on the black hole. But clearly, well, it depends now on what type of state I put the large masses. They could induce large fluctuations, much larger fluctuations on the small particle than the small particle can induce on the big masses, right? So it's just a matter of what is the state of the different elements here. Okay, is this clear? Questions? No. Okay, let's think about another example, which would be actually useful for for the actual calculation of the modified Hawking. So this was example 1. And example 2, this picture should be familiar to those of you who came to the previous lectures. You remember that picture? This was the shell, the collapsing shell, right? So it's collapsing. So this is the example 1 is superposition of macroscopic masses and example 2 is a semi-classical collapsing shell. So let's imagine that I'm taking a shell, a collapsing shell of matter, or I can take a collapsing shell of photons, right? That I can create in the laboratory. I arrange many lasers. Those of you who know the Austin Power movies can imagine how it's done. And I arrange them in a circle, right? And I shoot them simultaneously, so I get a collapsing shell of light. And in principle, that shell, if it's eventually it will reach its own Schwarzschild radius, right? If I have enough energy, the Schwarzschild radius will be large. For smaller energy, the Schwarzschild radius will be small. But nevertheless, I can create that, and I can put that shell in some quantum state, right? Now, in this case, I can imagine that the shell has a Gaussian wave function. So, psi shell say proportional to e to the minus r shell. So this is psi shell of r shell. Let me write it. So psi shell of r shell is proportional to e to the minus r shell. Let's say minus r bar of t square divided by 2 sigma square. Can you see what I wrote there? So, what is the meaning of the wave function that I wrote? If I had a particle, right, moving, first course in quantum mechanics, I have a Gaussian wave function for a moving particle. How would it look like? Like so, but with r replaced by x, right? You remember your first year quantum mechanics? So now think about this shell of photons that I'm creating in some quantum state. The position has some fluctuations, and the shell is on average contracting. Okay, so R bar is the average position of the shell. It is contracting, and it has some fluctuations around it, and the fluctuations are parameterized by the parameter sigma. Okay? So this, since we know that the shell is quantum, then generically this is the state that it will have if we arrange these lasers and create the shell of photons. Right? You agree? I have to make a big effort to set sigma to 0. Now, how would the classical shell, what would be the limit of treating this shell as a classical shell? It's not a rhetorical question, you can answer. Sigma goes to 0 in some units, and sigma goes to 0. And then psi shell would be approximately a delta function, right? But this is an approximation. We never have that for real quantum shells. If we set it like so, what will happen? What would the uncertainty principle tell us? If we localize this shell arbitrarily accurately, what does the uncertainty principle tell us? This you know. The momentum fluctuations would be very large, and so it will not continue to collapse as a shell, as a spherical shell. It will just disintegrate if I try to do that. I can arrange it so that, depending on the mass, that the width is very small, and the momentum fluctuations will also be very small, so I get essentially a Gaussian that widens a little bit in time. Just like the solutions that you find in first year quantum mechanics. Okay? Now, so if we want to repeat Hawking's calculation with a wave function for the geometry, one way of doing that is take a semi-classical shell and repeat the ray tracing procedure with a quantum mechanical shell. And in fact, this is what we did with Joy Medved, and I would like to show you this calculation. By this pace that I'm going, I think I will not manage to cover all the material that I wanted, but this type of calculation I want to show you because it illustrates the violent approximation of setting CBH to 0. Okay, so let me do that calculation now. And so what I would like to calculate is the radiation emitted by a semi-classical collapsing shell. And in this case, what I'll do is I'll take sigma to be the Planck length. The reason that I have some arguments showing why a shell that is collapsing should have that width, But clearly, this is, if we're just talking about gravity, this would be the natural scale which will appear. So let's just do it. If you're unsatisfied with this choice of LP, just work with the general sigma and see what happens. It will not be that important for us. So this is done in 2 recent papers with Joy Medved, and I refer you to the papers for the details. And I will try to outline it. So the calculation that I want to do is to calculate, to repeat this calculation. You remember that we did, the B's are creation operators for outgoing particle, and we did that in the Hawking case. And what we found was that we did it in a Fourier space, and we found that this was given by an integral and this was proportional to a delta function of omega minus omega tilde, and this was part of the proof that the Hawking density matrix is diagonal. So you get a mixed state in the information paradox. So now I want to write this in a slightly different way. I want to write this like so, and introducing, here a delta function in here. So I'm writing it like so, 0 to infinity d omega prime, 0 to infinity d omega double prime, beta omega prime omega beta star omega double prime omega tilde times e to the iv omega prime minus omega double prime, 1 over 2 pi. Okay, so if I just do the integral like so, the integral over the v will give me a delta function over omega prime and omega double prime, and then I go back to this integral. And the reason that I want to make this is that now I need to calculate the semi-classical analog of this function, of this expression, and I'm doing it in the background of this semi-classical shell with the wave function. And what I need to do, according to the board upstairs, is I need to replace the calculation of this beta coefficient, the Bogoliubov coefficient, by beta is C of, well, I change here, so I keep the order of my notes. So essentially the same expression. Beta is C of W double prime W tilde V shell then psi shell of V shell. Okay? So the rule of calculating the expectation value of a matter operator, so the matter operator that I'm calculating now is Bi dagger Bj. So B dagger omega, B dagger omega, B omega tilde. And now I have to evaluate the expectation value in the shell wave function. The shell wave function is a function, for simplicity, I took it to be a function of just one variable, the radial position. And that radial position is translated on this diagram. You remember well, this diagram is no longer valid, but I just remind you that the V was the advanced time coordinate, and V0 was the last time where a ray could escape to infinity. And I'm missing here another e to the I V omega prime minus omega double prime divided by 2 pi. So I just took this expression, and instead of calculating the classical geodesics, I calculated the expectation values in the shell wave function. Okay, is this clear? Very good. So now I can actually do the calculation because I have the wave function. I know how this, remember beta classical of omega prime omega was proportional to 1 over 2 pi integral from 0 to V0 e to the I omega prime V dV e to the minus 2I omega Rs. This we wrote as e to the I m omega. And then there was a log of V0 minus V. I neglect the constant here. And now what we find is that the beta semi-classical of omega prime, omega, and V shell is proportional to 1 over 2 pi integral from minus infinity to V shell e to the I omega prime V e to the minus 2I omega Rs ln of V shell minus V. Because you remember how the beta function, this beta coefficient was calculated. It was getting most of the contribution from the large phase shift when the mode was exiting the shell as it was reaching the V0. Okay? Now the position of the shell is fluctuating. So the phase shift is also fluctuating. And it is determined by the position of the shell and not by V0. So right? So in this case, we find that the semi-classical Bogoliubov coefficient is almost equal to the classical one, with this really one little difference that turns out to be critical. So that part is the same as before, right? And now I get, instead of e to the IV0 omega prime, I get e to the IV shell omega prime. If you think about it physically, it's clear that this is what you should get, but the calculation also shows that. So then, now we have to plug this result into this expression. So you see, before, if this was V0, it would go in here. I would shift V by V0. Since the integral is from minus infinity to infinity, this wouldn't change anything. I would get a delta function, and that delta function will induce a delta function in omega tilde. But now, in this case, I have V shell rather than V0. And so I find that in this case, rho SC of omega tilde, and V shell is proportional to a semi-classical integral, which is equal to integral from minus infinity to infinity. This is the only difference between the semi-classical and so having a semi-classical shell and having a classical shell is this factor inside the expression for the two-point function. So let me do this integral for you. So by symmetry, I turn this integral from minus infinity to infinity to an integral from 0 to infinity over cosine. And this is equal to 1 over 2 pi integral from 0 to V shell dv cosine V omega prime minus omega double prime plus a delta function of omega prime minus omega double prime. Okay? Now that delta function, when I plug it back to the original calculation, gives me the Hawking result. Because a delta function in omega prime, omega double prime, was the original result. And then I get an additional contribution that is not diagonal in omega prime and omega double prime. It connects different frequencies, and that when I plug that into the original expression, gives me a result that is essentially uniform in omega and omega tilde. So I have a matrix of diagonal contribution that is essentially uniform in omega and omega tilde. And its magnitude, the magnitude of this correction, is square root of CBH. This calculation, now you can do explicitly, and if you can't do it, you just look at the paper. It's done really extremely rigorously. Yes?
Do you use W and W tilde and W prime and W double prime interchangeably?
No. No, you see, because this is these W prime and W double prime are integration variables. So eventually, this is ISC of W tilde and W double tilde, right? That I have to plug in, perform the W tilde and W double tilde integrations. I know that if I get a delta function in W tilde and W double tilde, this will induce a delta function in W in W prime and W double prime.
So when you write rho semi-classical as a function of W and W tilde, and the shell,
Yes, that is correct.
and then the integral you put W prime and W double prime.
That is also correct, because the betas, you see the betas are functions of W prime in W, right? W prime in W, and W double prime and W tilde, and then there are integrations over W. So they are like internal legs, okay? So I actually don't confuse them now. And okay, now, is this magnitude correct? The answer is yes, because we expect for physical observables, we expect corrections that are order CBH, right? If I have a density matrix or a two-point function that has off-diagonal elements, they never enter into physical quantities that I need to take traces. So the off-diagonal element enter only at quadratic order. Or if you wish, you can ask by how much do eigenvalues of the two-point function change if I have a correction of order square root of CBH in the off-diagonal, and the answer is CBH. So this is the correct magnitude. So in general, the form of the two-point function now is it has the Hawking matrix, the Hawking result on the diagonal, and it has very weak off-diagonal corrections that are order square root of CBH. Okay? So you see, in this case, that the zero, or the exponentially suppressed terms in the off-diagonal, for the off-diagonal elements of the two-point function, that was one of the key facts that we used to show that the Hawking matrix, density matrix, is diagonal, now get corrections that are much larger than exponential, as we were arguing before. And this is a result of an explicit calculation. Now, it also turns out that the expansion parameter, this I will not explain in detail. I'll just state it, that when we calculate, for example, trace rho ij square, we see that the expansion parameter in this quantity, which is related in a way that I will state immediately to the Rényi entropy of the Hawking density matrix. So this actually goes like n rad CBH rather than CBH. You can, a heuristic way of thinking about it is that imagine when you have, let's say you have n rad particles that were emitted, the two-point function you can think as an n by n matrix, and the off-diagonal elements there are n square off-diagonal elements versus n diagonal element. So they scale like n square CBH, because each of them is square root of CBH, and the diagonal squares like n. So the ratio of n square CBH coming from the off-diagonal and n coming from the diagonal, this ratio is n CBH. Okay? And this, in fact, we see that explicitly. Now, since we are all expert in quantum information, we know what the Rényi entropy, what the participation ratio, and all of that, I can use that, and I can calculate the participation ratio of rho ij, right? So this is the effective number of a non-vanishing eigenvalues. 1 over trace rho ij squared. Where rho ij is this matrix. Okay? So I find in this case that this participation ratio, sorry, the purity. So let's first calculate the purity. So that's trace rho ij square, and then that we find that it is equal to 1 over n rad. So this is the Hawking result, plus 1 over n rad, let me write it like so, n rad CBH. So this is equal to 1 over n rad plus CBH. Now, I remind you that CBH is 1 over the black hole entropy. So this is 1 over CBH of 0 approximately minus n rad. So you see that these two terms are approximately equal at the page time. And in fact, we can calculate the participation ratio, and we can also relate to a paper to appear with Laszlo Alberta and Andrei Khmelnytsky and Joy Medved, that the Rényi entropy of the semi-classical radiation, semi-classical analog of the Hawking matrix is actually trace log of 1 plus 2 rho, where this rho is the rho that I have used. And so from here we see that the participation ratio, the number of non-vanishing eigenvalues of rho ij corresponds to the Rényi entropy of the density matrix. And we can now, using these results, compare what we have to the page model. So you remember the page curve that we drew yesterday? We had SBH of 0 over 2. When we had this curve, this was S, or H2 of page, right? You remember that. We calculated it, I think, yesterday. This was the page time, which was SBH of 0 over 2. This is n rad. Right? Axis, and this is H2 axis, and this was the page result. And I'm claiming now that this participation ratio of rho ij that I can calculate from the purity here is the quantity that I should compare to the Rényi entropy of the density matrix. And so I draw here our participation ratio in quadratic curve that goes like that. It peaks at SBH of 0 over quarter, and it starts to go down at the page time. Okay? And if we draw the information curve, you remember the page information curve was essentially 0 up to the page time. And then it was going up at a rate of 2 all the way up to SVH of 0. And here we have something that is softer and asymptotically comes here. So this is ours. Page. So what this graph is telling us, in this case, that we have more information in the way that we are setting up the experiment of watching the black hole evaporate than in the page case, right? This is, you can see it from this picture. In the page curve, the first bit comes at the page time. Here, our first bit comes out much earlier. And in general, the amount of information is bigger in our case than in the page model. And the reason is clear. In this case, we are actually measuring correlations not only among the outgoing radiation with the assumptions that they are random, but we're actually measuring them or think that we measure them. And we also have correlations between the outgoing radiation and some of the ingoing modes included in this. This I don't have time to explain, but this is the reason why our the entropy here is lower and the information is bigger. Okay. Question about that? No. Okay, so since I don't have too much time, let me now explain try to explain quickly this point. I cannot present as detailed calculations that I did in this case because of lack of time, but should be able to find these calculations here in the papers. But the idea is very simple. So now we have to go to the pair production picture, right? Because we need to think about the near horizon state. We need to go to the pair production picture and to try to think about the near horizon state. And the important thing, as I said, that the black hole is time dependent. So we have the shell or the black hole. It has some wave function. The pair production picture we can think about, right? You remember about the W's and Y's or the P's and the Q's. And what should happen is that in this case, the pair is produced, and eventually the negative energy particle falls into the black hole. Because it has negative energy, it reduces the mass of the black hole. The positive energy particle escapes to infinity, and the black hole shrinks. And from an outside observer perspective, she sees the radiation going out and the size of the black hole shrinking. Right? Is this clear? Now, I can try and calculate these modes in the Hawking picture are produced in parallel direction to the horizon. Because they're, well, we didn't really explain that, but formally they stay an infinite amount of time near the horizon. That, of course, is unphysical because otherwise the black hole would not decrease in mass. But of course, in the Hawking picture, it doesn't because the mass is infinite, so everything is okay. But for a physical black hole, it has to decrease in mass. So these modes have to remain for some finite time in the near horizon region and then go away. But when they go away, they don't affect the near horizon physics. It's only when they are near the horizon that they're affecting it. So there is a finite number of pairs at each given time near the horizon. And the question is, what is this finite number? That finite number is the way that we can convert the amount of disentanglement to energy density. And we find, in this case, that the number of pairs is the square root of SBH. And one way of thinking about this is we think about the shell of the black hole as having some width, wave function of width LP. And now the wave function is the shell size is decreasing in time. It is collapsing. And I now ask, how much time does it take the shell to move such that at a later time it doesn't overlap with the previous one? So essentially, if I was looking at an atom, this would determine for me the coherence time of the emission. Because I have the wave function. If the wave functions are orthogonal, the emission is incoherent. If the wave function overlap, the emission is coherent. And in this case, we find that the number of emitted particles here has to be exactly for the black hole to decrease in size by L Planck is exactly n pairs. And in terms of time, the coherence time in Schwarzschild units is Rs squared over Lp, which is much larger than the Planck time, but much smaller than the typical evaporation time of a black hole. So essentially, we have a finite number of negative and positive energy modes that are near the horizon. And using this estimate, we can calculate the energy of the near horizon region. And in this case, where is it? The energy density is proportional to the number of pairs. And in this case, let's see. Yes, so it's proportional to the number of pairs times the energy per pair. Now, the energy per pair depends on whether the state of the produced pair is in thermophile double or not. If it's disentangled, the energy is finite. And then what we find is that using this number of pairs, the energy density is 1 over Rs squared, 1 over Lp squared. Okay, which is an energy density that is higher than 1 over Rs to the 4, so higher than thermal, but still low. And if the number of pairs would be SBH, so essentially there would be a time where the number of pairs would be of order of the total number of emitted particles that the black hole emits, as in the Hawking case. Then in this case, E would be 1 over Rs squared LP squared times Rs over LP, which is a firewall. So in this case, it's 1 over Rs LP cube. So if you think about that, it means that we have a Planckian energy density essentially near the surface of the black hole whose size is 1 over R squared. Okay? So what you see is exactly what I was alluding to before, that to convert the disentanglement of the near horizon region to energy, we need some scale. And that scale, in this case, is the number of pairs, or CBH, or the mass of the black hole. And when it is finite, the number of pairs is finite. And then it becomes a quantitative question, how big it is. And what we find is that, in this case, it is still parametrically small than Planckian. Now, in this case, it also doesn't violate the equivalence principle, because we are making lots of measurements and those of the outgoing radiation, and those measurements must involve interactions that are not gravitational. And so we are not violating the equivalence principle. Had we not measured the outgoing radiation, we would get an energy density which is much smaller, which is what you expect in quantum mechanics. If you're projecting on a state, the state itself, the state itself could change. Okay, so this picture fits what I know about quantum mechanics, and as you can see, has the potential for relaxing the issues that we encounter when we think about an infinite mass black hole. Okay, so let me summarize. I went a little bit over time, but I used this little corner to summarize my 4 talks. So the summary is very simple, right? So if we take CBH equal to 0, so the black hole as strictly classical, we find, I still have 10 minutes. I forgot that. I thought that, let me summarize and then do the redshift, okay? Because I already started. So black hole is strictly classical. And then in this case, we find that if we keep unitarity, right? This means that I have to break the equivalence principle, and if we keep the equivalence principle, unitarity is broken. Right? This is what we saw in the first 3 lectures. So the message is I think, very clear. Treat the black hole as a quantum state. which it is, right? Every object in our world is quantum. So if we want to treat some object as classical, we know that it is an approximation, and we have to justify the approximation according to a specific calculation. The parameter that determines the quantumness of the black hole is the ratio lambda BH over 2 pi divided by Rs. And this is finite but small. And then the issues that we encountered, we saw a more detailed example with the Hawking calculation showing that the density matrix is not diagonal, and nevertheless the energy density near the horizon is not very large. And there are additional quantities that we can look at, and we see that in this case the issues are relaxed. I can't say yet that all problems are resolved because there are still some calculations to be done, but at least there's a framework where these calculations can be done, and we see that the finiteness of the mass of the black hole leads us away from the negative conclusions that we had here. So my personal conclusion is that this is the right way to go, and we simply need to understand the consequences of treating the black hole as quantum. So let me, because I have a few more minutes, let me do the hair, okay? Because it's actually a piece of a very nice classical calculation. Any questions about what I just concluded? No? Good. So let's do the hair. So the idea of no hair theorems, or that black holes have no hair, I think you heard a little bit about it from Gia, right? That the black holes are characterized only by masses or charges. We will be interested only in neutral Schwarzschild black holes, so let's do that. So let me very quickly show you or prove to you the no hair theorem. So let's take as a kind of hair a scalar field, and we ask whether we can find out about the scalar charge of a black hole. So for that we need to look at a classical scalar field that satisfies the Klein-Gordon equation. Let's take a massless scalar field, doesn't matter in this case. And this G is the classical Schwarzschild geometry, and we know that this is 0, and then phi of infinity is 0. This is our boundary conditions. Okay. Now let's compute. So in this case, ds square is and then f of r s is 0, and f prime of r is not 0. So I'm looking at just the standard Schwarzschild black hole with the f of r is, we know what this function is. And now, let me integrate this equation from Rs to infinity, dr times phi. So then I have here dr square root of g, grr, dr phi. Okay? So I took this 0, I multiply it by phi, and I integrate it from Rs to infinity. Okay, clear? Very good. So if I integrate a 0, I should get a 0. But I can integrate by parts now. You see this dr. And from that, I get that 0 is equal to minus integral from Rs to infinity dr phi square r square f of r plus integral from Rs to infinity dr of phi r square f of r dr phi of r, dr phi. Okay, I integrated by parts. And now I find that in this case, f of r, right, r squared, phi prime, between Rs and infinity is equal to the integral from Rs to infinity, dr phi square, r square, f of r. Okay. Now what? What is this quantity? The left-hand side? 0, right? It's 0 at infinity because phi vanishes at infinity, and it's 0 at Rs because f vanishes at Rs. Right? So this is 0 equals this. Now, how could this equality be correct? Here I have a positive semi-definite quantity, right? It's a square, r square, f of r. So what do I conclude? Come on. What do I conclude? This side has to be 0, right? Yes. So phi is constant, right? So dr phi has to be 0, so phi is constant. And what is its value? 0. Right? Because at infinity it was 0. So this means that I cannot excite a scalar field, and I can do, of course, with a gauge field, this type of proof doesn't work because the A0 is not a gauge invariant quantity. But with any field that is not a gauge field, this type of proof works. So I see that the fields in the background of the black hole cannot be excited. Which means that since, let's say I created this black hole from 5, I cannot know what was inside them, inside the black hole. So this is called the no-hair theorem. Now, how do we evade the no-hair theorem when we have a semi-classical or a quantum black hole? Right? In this case, we have to, as we did before, we have to take the expectation value over fluctuations of the position of the horizon, right? And when we do that, the expectation value of that position, as we were discussing with the redshift, will not be 0, because it will always get contributions from positions where it's non-vanishing. So this side, when we take the expectation value with the black hole, will not be 0. And then we will be able to get some hair. Of course, the hair will be suppressed. It would still remember that there is a region of very large redshift. So it will take a long time to emit the hair, to shed the hair, but that's okay. As long as it's not infinite, we're doing fine. Okay, so I think with this high note, let me stop, since I already concluded. Thank you very much.
Do you have more questions?
You consider the shell which is changing in the wavelength,
It's fluctuating.
fluctuating but not
Just a spherically symmetric shell. I could do something more complicated, but this is demonstrating it's demonstrating the point.
the mass is constant.
Mass is constant.
The point is the geometric field, the geometry outside the shell does not depend on the size.
Of course it does.
No, it depends only on the mass.
No.
Because this is Bertov theorem or something. It says only you do not have to know whether
This is for solutions of the Einstein equation, but these fluctuations, right, are not solutions of Einstein equations. So the Birkhoff theorem in this case does not apply. You are looking at an off-shell. In this case, it's an off-shell geometry. It's in the same way that you remember where are the two masses. If you did the two masses there, and you were looking up, let's say you had a spherical distribution of mass, and you would look at that, you would say again that the geodesic will depend only on the mass, but clearly it doesn't, if you think about it physically.
this also, I do not understand. What is your answer if a mass has two different positions, in quantum sense?
So in this case, we have to, what I'm proposing in this case is that we would take a superposition of geodesics and calculate the quantum average of this motion. Is what you suggested. Well, that's the only rule that I can, in this case, it's the only rule that I know that quantum mechanics is telling me to do.
It could also be that a test particle moves in a classical trajectory along some every field.
But this is, so in fact, this is, I think, the mistake that Penrose did. Right? So Penrose concluded from thinking about this type of example that the equivalence principle and the superposition principle of quantum mechanics are incompatible. Because he wanted the particle to continue to move on a single geodesic. But in this case, it cannot.
So the particle becomes a quantum particle.
Yes, this is the inverse of the back reaction that I was telling about. See, if we accept back reaction, if we accept that a quantum particle can affect a large mass due to its fluctuation and that mass becomes quantum, why shouldn't we accept the fact that if I have a large mass that is fluctuating, the trajectory of a particle will move? It's the same thing that we have for a quantum electric field, right? So consider a situation where you have a quantum electric field and you have a motion of a test charge particle in that field. How would it move? To calculate its motion, I would need to take the expectation value in the external field of the motion of the particle. These are the rules of quantum mechanics, right? This would be the semi-classical a prescription that QED is telling us to follow. Now, in the case of so-called quantum gravity, as Gia was saying, we do have a theory of quantum gravity. If we apply it to scales that are much larger than the Planck scale, it is better than QED, and it is telling us to do exactly what you were proposing to do. So in this case, if we follow the rules of quantum mechanics, there's a non-ambiguous answer, and in this case, Penrose, in fact, is incorrect in saying that the equivalence principle is violated because we have another scale here, which is the quantum wavelengths of the background masses, and that quantum wavelengths is entering into the equivalence principle as a new scale and is modifying what the equivalence principle is telling us. So that's okay. There is no problem with the equivalence principle here.